my email out of the way. You guys keep close my email. Don't want email, come on. Don't give me fatal error. And oh, I had it open a bunch of time. There we go. Okay, so a few things, guys. I'm gonna go over these tiny little slides, and then Spencer, my friend, if you don't mind, I will go over a couple of tables in the NDC code book by firing my NDC code book. Just a quick reminder, guys. In the NDC code book, there is certain wiring, conductors, and insulation approved by the NDC code book. Other than these ones, you cannot use. And I'm going to remind you, this will be a reminder. So this will be your T, H, H, N, and this basic will be your cover, Cu, or aluminum. Basically, between these two, THHN, cover or aluminum, and THW, Brad, my friend, between THHN / THW and cover or aluminum, you have covered basically 90% of the wiring methods in any code book. Between these two insulation and these two conductive materials. When we size conductors, guys, we size it based the single most important table 310.16, which changed, but we care less about this one now. So 310.16, I'm going to go walk you guys very quick how to size based on 310.16. I want to remind you, my friends, of the following. When we size based on 310.16, the following you have to do. Number one, size based on sizing. First, based on continuous. Number two, based on voltage drop. And number three, based on derating. I can't emphasize, I teach this one to the exam prep guys, the guys who sit for master and journeyman. This is dear to the heart of the State Board of Electricity, so it should be dear to your hearts, because that's how we size in the NEC code book. We size based on continuous load. Anybody guys knows if it's continuous load, when we size a cable, what do we do? Thank you, 1.25, that's very easy. 1.25 times the load. If it's voltage drop, guys, we have to size based on the voltage drop. Derating, I'll go to voltage drop in a second. For derating, guys, you're going to go to table 310.16, and there's two ways we derate. We derate based on number of conductors plus temperature. We derate based on number of conductors in a conduit and temperature. And you guys have done a few derating for me over the years. Voltage drop, we size based on voltage drop. Becomes a big issue, Spencer, if you have a parking lot, if you have a long calculation for three-phase, voltage drop equal, it becomes, here's the formula that you're going to be using, MC, or CM, circular mill, CM equal 1.73 times KIL, K-I-L over voltage drop. This is the formula that we use to size based on voltage drop all the time. CM is a circular mill. Voltage drop, always assume, when we do voltage drop sizing, guys, we always assume it's 3% voltage drop. So, Brad, if your system is 480, multiply it by 0.03 and put the number over here. So that's my voltage drop, 1.73. Anybody can tell me why 1.73, guys? That's a three-phase, thank you. And I always emphasize three-phase because we're commercial now. Everything that we do is three-phase. K is a constant given, guys, at 12.5 or 18. This is always given. I is the current, and L is the length in one direction. So that's one formula that we size. And then the other nicer formula that I like personally here, guys, is to rel over 1,000. Voltage drop to rel over 1,000. So, which is 2 rel, R-I-L, over 1,000. That will give you a voltage drop. So, which is basically R equal to size based on that one. I'm just trying to flip it in my mind here. I'll write it for you. Voltage drop equal to so times that will be voltage drop times 1,000. Divide this. So 1,000 divide this by 1.73 times 1.73 times rel, RIL, so this is I and this is L. This is another very interesting formula, Spencer, that we size based on voltage drop. It's rel over voltage drop multiplied by 1,000 divided by 1.73 times IL. Basically, you're finding the cross-section area of the conductor. So if I give you guys a voltage drop is always 3% on feeders multiplied by the voltage. We will take a couple of examples about this one, guys. Divided by 1.73 IL, everybody knows the length and the current that's a conductor is going to carry. And then you find R. When you find R, guys, you can go to table 8, chapter. When you find R, after you find R, you're going to go to chapter 9, table 8. And based on chapter 9, table 8, you size your conductor. The same thing, guys. CM comes from chapter 9, table 8. That's how we size the conductors. Very easy. Suppose you have a 480 system. You need to size an 100 amp and the length is 500. So voltage drop is 3% times 480 times 1,000 divided by 1.73 times. The current is 100 times 100. The length is 500 times 500. You do the calculation. You come up with 0.53 ohm. So you go to table, chapter 9, table 8, and find a conductor that can have this resistance or less. This resistance or less. We will do a calculation based on that one. But my emphasis, guys, here, I hope you listen to Chad. I know you're getting sick of Chad talking to you guys. I hope you emphasize, when we size any cable, any branch circuit, any feeder, any service, we always look at three things: continuous load, voltage drop, derating, and whichever method gives you the bigger size, you always use. Example: if I size based on continuous load and I came up with 4 aught, voltage drop gave me 3 aught, and because of derating, I came up with 1 aught. So 4, 3, 1. Which one do you think you should use? The 4, the safer, the bigger conductor. So we use them separately, these methods, and we size based on the one that gives us the largest conductor. I know we've done this, and I know we've done this one, and this one that's coming, guys, we'll do a few calculations about voltage drop. That's how a person has summarized the whole sizing, gentlemen. Any question, my friends? Any question? And I promise you we'll do calculation on that. Let me take a snapshot of this. So that's the length, the diameter, and so forth. I always like to show this one, guys. If you now we are becoming 3-phase guys and gals. The reason, guys, they always tell you group the circuits. You guys remember how we said if you have a circuit, here's phase A, and here's phase B, and here's phase C, and here's the neutral, right? The reason, and this is the conduit that's carrying them. The reason that why they always say, guys, you have to group the 3-phase and the neutral in one conduit. If you guys look at these are how the sinusoidal phases, sinusoidal signals for every phase. So suppose that this one was phase A, this one was phase B, and this one was phase C. And these are each one of them, guys, without getting too technical, each one of them is 180 degrees out of phase with the other one. Long story short, if you guys group them together, the magnetic field of every phase will cancel the other phase. Who cares? Muhammad is sitting here and say, Chad, who cares? If when the magnetic field cancel each other, it's reduced the impedance of the circuit. The circuit has a major concept, guys, called impedance. Impedance of the circuit. Just remember one thing: the impedance of the circuit is minimized as you group the conductors together, and also there is no inductive heat. Remember how the term inductive heat when we group them together. So when we group them like this to minimize impedance, number one, and also eliminate, if I spelled it right, eliminate induction heat. So DJ, my friend, why do you care about eliminating the induction heat? If you have one conductor in a steel conduit, that conduit actually become a heater. So imagine putting a conductor and a heater right around it. Then of course your insulation is going to deteriorate over time, and you're going to have a short circuit. Why do we care about minimizing the impedance, Spencer? The smaller the impedance, the further you can shoot the voltage. The further you can shoot the voltage. How do you minimize the impedance without getting into the calculation, the engineering calculation? All what you have to do, always group phase A, phase B, and phase C, and a neutral in the same conduit. That's all what you have to worry about. Group them always in the same conduit. Always in the same conduit. By grouping them, guys, two things. You minimize the impedance of a circuit, and number two, you eliminate the induction heat. The induction heat. Any question about these two concepts? If you wanna research it in Google or something and go induction heat and three-phase impedance, just FYI, guys, when a current goes through an AC conductor, there's three impedances that this current is gonna face. One of them, Brad, you know it all the time, the resistance of that conductor. That we all know. The second one, guys, is the inductive reactance. The inductive reactance is a function of how the wire is moving through the conduit. So it's basically like coil. If the wire is coiled, the more the wire coiled, the more inductive reactance you're going to get. Or the longer the conductor goes, the more inductive reactance you're going to get. And the third one is capacitive reactance. A capacitive reactance, guys, if you put a conductor, if you put just, and I don't want to go there other than just mention, if you put a phase A here and a steel conduit around it, you know what we have done? You created a capacitor, right? Here's the positive and here's the negative, which is grounded. The conduit is grounded. That's like negative. And the positive is the hot wire inside that conduit. You created the capacitor. And believe it or not, if you put one conductor in it, that capacitive reactance, they call it, it reduce the voltage. It create impedance. It create resistance to the flow of the current. So this is as far as I want to go. Reduce the impedance. The impedance, just FYI, if you guys remember from the day of the Riemann, the impedance is R, one component, and XL, and also XC. This is resistance. This is inductive reactance, and this one is capacitive reactance. Without getting into the engineering part of it, guys, all what you have to do is just group them, and you're guaranteed no induction, not guaranteed, but you minimize no induction heat and reduction in your impedance. Any question, guys, about this? Why do we care about reducing the impedance, guys? Reduce the impedance will reduce the voltage drop on my runs. Resistance, inductive reactance, capacitive reactance. Any question, my friends? So that's what I want to mention here about that particular one, how important it is, Mr. Rabab, to group the systems together. I took a picture of it too. Current, I don't want to talk about single phasing. Conduit heat, we talked about conduit heat, guys. Here's where you create a capacitor here. Here's your positive, here's your negative. You're creating basically a capacitor, and there's current, believe it or not, that's going from here to here. That's how you heat your conduit. That's how you heat your conduit. Okay. Another thing is this chapter, and I'm going to go to the table in a second here. Just want to go over these. Voltage drop, KCM. The other thing, guys, is paralleling. When we parallel conductors, I want to review the parallel rules for you because you're doing it. Paralleling. Rule number one, same material. Number two, same insulation. Number three, same length. And number four, so we have material, insulation, length, termination. Same termination. Number 5, same conduit, if any. Did we forget anything? Same material, same installation, same length, same termination, same size. The number 6 is same size. These are dear to your heart, and it should be dear to everybody who deals with power, guys. When we parallel conductors, you're going to use and you guys can see how the conductors here are parallel, right? Look at this conductor. Phase A came from here, phase A came from this conduit, and phase A came from the other conduit. Can you guys see that? And the same thing, phase B and phase B. Oops, that's phase B coming from here, and phase B coming from here, and the others are actually phase, the last 3 are phase C. The last 3 are phase C. If you're paralleling, you're looking at 6 rules. You cannot, as a matter of fact, in the power, you can add a 7th rule that I always like to remind people is minimum of 1 knot. So regardless of what you do, you can't parallel less than 1 knot. 7 rules for paralleling. They're located in NDC code with different locations, but 7 rules when you parallel conductors. Any question, my friends? Any question? Any question about the material? If you're paralleling either copper or aluminum, insulation THHN or THW, but they all have to be either THHN or all THW. Length, they're all 100 feet. Termination, they're all terminated with the same lug, type of lug, same conduit, EMP, rigid PVC, same size, 4-aught, 5-aught, 500 kcm. Is there a 5-aught? No 5-aughts in America. Minimum 1-aught, of course, is the minimum that you can size. Any questions, Sir Bev? When you parallel, my rule of thumb, please, rule of thumb, when did you start paralleling? My rule of thumb is always after you hit kcm. If you can't carry anything with up to 500 kcm, that will give you amp-wise 380 amps. If you can carry things up to 380 amps, 500 kcm, good. Anything higher than this, start paralleling. So basically, anything higher than 400 amp, you start paralleling. I'm going to call these 2 guys start point. Start point. Any question, guys, about the paralleling? I know this is a quick review of the paralleling conductors. Last thing for the project managers among you guys. When you do building, did you guys, where were we? Commissioning. Did you hear the word commissioning? When you have a 4,000 amp switch gear, I think Jim was talking about commissioning. Was he? When he was here, Jim Rasmussen? When you install a 4,000 amp switch gear with large UPS system and PDUs and transfer switches, good companies go with higher okay, we design it, like Michelle Cooley will design it. Hunt Electric will install the system, or Egan will install the system, and then X company comes, the third company, guys, electrical company comes and do the commissioning. Commissioning, Mr. Beb, is detailed point-to-point operation manual testing. I think, yeah, if you guys remember when we went to Boston Scientific, they were talking about commissioning the building. And what they do, guys, is they bring, those guys are not electrical inspector, and they're not electrical contractors. They have machines, they have every machine that you can imagine. And they go and they say, okay, this is this transfer switch supposed to transfer within 3 cycles. Okay, let's go put a load on it. They put a load, literally a load on it, and they push the button and they time it. Is it going to transfer within 10 seconds like you said? If it transfers, check, yes. Is it going to go back within 15 minutes as it's supposed to? And they wait for 15 minutes, guys. If it goes back, check, it works. So they go verify every single operation, and they write an operation manual for the owner. We did a data center for Target stores, and we have a company walks in and it tests every single things after the electrical contractor finished the work. And then they give an operation manual for the owner, how things are going to work, and that things are working. So commissioning. Cool. I can't remember the name of the companies, but if you go commissioning, company commissioning, it's basically detailed inspection. Not just inspection, detailed testing and inspection of every single generators. They go to they fire the generators. They say you have 4 generators sitting right there. Okay, let's go fire them and see if they work. And are they going to transfer? Are they going to pick? So they really go guys through step by step how the system is going to work. So if you are in this, the reason why I said that one, if you're in this, if you you want to pay attention to what I'm going to say next here, they have a machine that's called Migger. This is an old Migger, guys. They have a machine like this that's called Migger. What they do for that machine, a lot of you guys would never use it unless you are doing commissioning or you're a project manager on a project. If you guys are project manager, when the project is done, before they energize the 4,000 amp switch gear, they're going to go to a Migger, which measures the impedance. Look at that. They grab phase A, really cool, phase A and phase B. And they send the signal through phase A and phase B. And Spencer, you know what they're looking for? They're looking for short circuit. If the impedance between phase A and phase B shows infinite, huge amount, this means the insulation is 100% perfect. But suppose inside this conduit, right in here, it's shorted, right? The 2 phases are shorted. Because when you pull them, you damage the insulation, and the insulation is really not just actually shorted, guys. If the insulation is, say half of the insulation was cut, not shorted, half of it is cut, the Migger will be able to tell you that your insulation at a certain point in this run is actually is damaged, is compromised. So you have to do, you have to go pull the conductor and look at the insulation. So these, the Migger phase A to phase B, phase A to phase C, and phase C to phase B, and they also measure the conduit. They want to make sure that when between the conduit and phase A, it's infinite impedance, guys, meaning there's no short. And the same thing between phase B and the conduit, phase C and the conduit. So this machine, this is one of many machines that they use, guys, to commission a building. So FYI for you, Spencer, you would never be unless you work with a commissioning company. And by the way, to work for a commissioning company, you do not have to be an electrician. You know, you don't have to be an electrician because you're testing equipment. You're not installing them. So it's really nice. But pay attention to the word Migger and what they're doing right here, guys. If you look at the couple of, they're testing the installation. This is how to test the installation. Mr. Rubeb, we as electrical engineers, we care about THH and conductor, 4R THH and conductor. But you send somebody like DJ, half a banana electrician, to pull all these 500 kcm conductor in a conduit, and he's so mad at his boss. While you're pulling it, you cut half of the insulation of this THH. Now what happened to you? Compromise the integrity of this 40 to 50 year old cable. That's supposed to be 40 to 50 year old cable. Sit there. You damage the, you compromise the insulation. Unless you do commissioning, Miggering like this, you would never be able to find it. Never be able to find it. That's basically the good stuff about commissioning. The major stuff that even contractors, Brad, will do it if they don't have a commissioning. Miggering is a big deal on feeders because the last thing you want to do is you go flip the switch and you close on a 3-phase short circuit because an electrician forgot and he bonded phase A to phase B. You know, an apprentice accidentally bonded phase A to phase B. It could happen, right? And what you do, you go close a 4,000 amp switchgear switch, and half of your switchgear is burned before you even hand it over to the owner. So Miggering is a big deal, guys. It looks for short circuit, mainly short circuit and insulation. Test for short circuit and test for insulation. It will pick up any ground fault or short circuit in the system, and also so you measure for short circuit, number 1, number 2, ground faults, which is ground faults, and number 3, integrity of insulation. The integrity of the insulation. The integrity of the insulation. If I spelled that right. Any question, guys, about this? Again, you really, if you work for Michelle Cool Erickson Band, you'd never worry about that. Only if you're working for electrical contractors, and as a project manager, pay attention to the Migger. Mega is one machine. They have guys current generators. They call them current generators. Load banks. They have tons of other machines. Current generator. It pumps 50,000 short circuit in the panel, and it makes sure that is the mains gonna trip if I put 50,000. Okay, you said you are an engineer. You said this is gonna trip at 50,000. Let's go generate 50,000 current, and they have a current generator. Pump it into this panel. Um, and watch the circuit breaker, bam, tripping. Is it tripping on time? Is anything burned after it trips? So they verify everything, guys. So it's really cool. I think it's cool. So that's what I wanted to show guys about this chapter. The second thing I want to show you guys is a couple of tables dear to my heart, and I hope it's dear to yours too. If I go to, is this my, there I go, my, nope, that's this one. I'm gonna fire my NEC code book, guys, and if you be generous enough just to, and I know some of this is reviewed for some of you guys. Okay, 310.16, and I'm gonna go all the way, guys, to a couple of these. There you go. This is my first favorite table. If you guys, it changed in NEC 2010. They moved it at the end of the book. If you guys have, if you don't know this table, please pay attention to it. Brad, you're working for a fire pump, and you're going to wire a fire pump. You need a fire rated wiring system. Fire rated wiring system. We're going to find a fire rated wiring system. On my conduit, guys. If you look at my conduit, on my cable here, minerally insulated, this is a very common wire to wire for fire pumps. If you have a fire pump and you want to wire it for the fire integrity of that cable, my cable would be your favorite insulation. So this table, guys, which is 310.13a, change the name. It will give you a few things if you don't know. The operating temperature, the maximum, applications, dry. Mainly in this one, I can use it dry or I can use it wet, guys. It's rated for 90 degree, and under special conditions, it's rated all the way up to 250 degree. The installation time, and the smallest and the largest size that you can buy it from, and a couple of other things. So this is, please know how to use this table. Very handy. And I know we touched on that one before. I highlighted on my cable because this is one of the ones that you use for fire pumps if you need a fire rated wiring system. Any question, guys, about this table? So I'm going to highlight a few of them. On my cable, please remember it with fire pumps. The second one or two, I'm going to go RHH, dry and wet location. This is another insulation gem, my friend, that also they use inside RHH, rated for 90 degree in damp or wet location, damp or dry location. You can get that baby up to 2000, from 14 to 2000. This insulation is also one of good insulation that they use, guys, for emergency feeders. So if you have an emergency feeder and you want to put this emergency feeder inside a conduit, and you need it to be fire rated conduit because it's an emergency feeder, you use an insulation RHH. Please highlight this one. It's not a damp, it's a damp or wet location. As you can see, it's not damp or dry, it's not wet location. If you need that baby to be wet, here's your baby. If it's wet, that's the one I'm going to be using, RHW. And Brad, my friend, if you say, Chad, I want one that's rated for 90 regardless. There you go, here's one for you. This is RHW-2, rated for 90 degree in a dry or wet location. No matter what in a dry or wet location, rated for 90 degree. And look how big you can get this cable, guys, from 14 all the way to 2000. Please be aware of this. Please know how to use this table. And I'm highlighting one of the most important ones. We're talking about fire pumps here. These are the wiring system that you can use fire pumps between MI cable and these two installations. Any question, my friends? Any question? So I'll grab a couple of others as we move through. So this one, Look at that. There's SIS they use inside the switch gear. There's everything. Here's my favorite, THH and your favorite. I'm sure you guys by now. THH, 90% of you guys will be ending with THH. It's rated for 90-degree dry or damp location. You can buy this baby from this all the way to 1000 kcm. That's almost, remember we parallel. Remember guys, we parallel. So that cover you 4000 amp switch gear, no question asked, because we parallel. If you are to install it in a wet location, Spencer, underground PVC, please be aware that you have two options, THW or THHW. I would use for THHW. The only difference is if in wet location, it's size 475. In a dry location, it's 90. And by the way, guys, the 90 is meaningless. 90 is meaningless unless you are derating. Unless you're derating. The 90 doesn't mean anything. Unless you're derating. So please highlight this one, guys, if you are not aware of this. Look at that. I can THW. I can buy it all the way to 2000. A lot of people, guys, contractors buy an installation that says THHN/THW. So Spencer, they carry one type of conductor. You can use it inside. It will be rated for 90. If you're using it outside, the same conductor, because it's double rated. Use it inside or outside, no problem. Can I use a wet location cable in a dry location? Yes. So please, if you don't know these guys, please highlight them. Again, anyone that starts with two guys, if you need something THW in a dry and wet location, no problem. If you use THW-2, it's rated a dry and wet location. The most common ones, guys, THHN, THW, or THHN/THW. Any questions about these? Do I trust that you guys know how to use them? They're there, know where they are? Okay. Now, the insulation that a lot of people, some people, guys, okay, so you can use THW and -2, dry and wet location. I'm not going to talk about UF cable. This is for residential. We talked about UF cable and USC cable and US2. 1-2 installation I'm going to bring to your attention, guys, is X, the X's. These are also, some people use the X's here. Here's an installation, XHSW. It's rated for 90, dry and damp location. If you use the 2 next to it, regardless it's wet or dry, it's rated it's wet or dry, rated for 90. If you use the first one, it's dry or damp location, goes with 90. 75 goes with wet location, as you can see. And I want to bring to your attention, guys, the sizes that these babies. There's big sizes here. These are big sizes. Any question, my friends? Any question? So these are basically the most common ones. If you are lucky enough to work on a high temperature wiring system, I'll show you guys in a second. So this is very special application, the Z installation. Very few guys will deal with the Z installation. Z installation, guys, you can use it up to 150 degrees. Look at that. And ZW2, you can use ZW up to 150 degrees. These conductors, they call them high temperature, Spencer, high temperature, very special application. Say you have a boiler room and the boiler room is extremely hot and you want to bring a feeder to the boiler room. You need your conductors to be, and to durate and so forth. They use Z and ZW and ZW-2 and so forth. Any question, my friends? Any question about these? Special application. So I'm going to make sure that everybody guys knows that one. Okay, so that's a table, the most important table that you're going to encounter for derating, and I'm going to move quick here, and you're not going to hear Chad talk about this again. If you don't know that for derating we use this table, please be aware of it. This is the table that we use if there is more than 3 current carrying conductors in one conduit. Example, if you have more than 41 conductors, you cut them 35. So if I have a conductor that can carry 100 amp, the same conductor, if I put 35 in one conduit, now I can only suck up to 35 amps out of it. You're dead. Anyone does not know how to use this table to do it based on bundling. Any question, my friends? The last time you're going to hear Chad talk about this one before we send you back to the industry. So this table is very important table. Everybody knows how to use it, and I'm moving fast on these because a lot of it is review, guys. We've done it over the last 2 quarters. Temperature came in 2008. This one, guys, came in 2008. If you are putting fins on the top of the roof of a building, you have to add temperature adder. For example, if I have a conduit coming and my conduit is sitting right here on a commercial roof, and that stand here is, let's say, 12 inches. I have a 12 inches stand, and the ambient temperature right here, guys, is 90 degree Fahrenheit ambient temperature, and I put it on a roof on a block that's 12 inches. So for example, 12 inches will come all the way up to here. Here's my 12 inches. Then Fahrenheit, I need to add 30. Then this becomes 30. Add 30 Fahrenheit, 120, right? Degree Fahrenheit. It will change your derating based on 120 Fahrenheit. Any question? Temperature adder. Temperature adder. Anybody does not know how to use this table, guys? Temperature adder. If you have a chiller, Brad, on the roof, pay attention to this one. A lot of people, guys, put chillers on the roof and they put feeders going to the chiller. Pay attention to this particular one. Any question, guys? Who cares about this? Now you can derate more. They want you to derate more. So that was brand new, guys, in 2008, and it's still in 2011. No changes in 2011, my friends. No changes. Okay, and please let me know if I'm moving too fast. I know we have covered these. This one, I hate to mention it, but this one, guys, is basically for engineer. This one is for residential, so please don't even mess with this one. Residential. So when we go commercial, industrial, what do you do with this table? Out the window. You don't even look at it. Engineering supervision, guys. Under engineering supervision, conductor application shall be permitted to be calculated by means of the following general formula. I want to bring to your attention, guys, this one. Now we are in a commercial industrial. Please pay attention if you're sleeping to chat this time. You see this formula, guys? There's a software called AmpCalc. You can research it, AmpCalc. You'll find it. It's $1,000. AmpCalc. AmpCalc. I believe this is how it's spelled. They use this formula, guys. This formula to find how much current a 500 kcm conductor can carry under these circumstances. How can they do that? And then you don't have to go to the tables. How can they do that? See the word? Engineering supervision. If you work for an under engineering supervision. By the way, Brooks, if you guys have PE engineers, which I'm sure you do at Egan, it could be engineering supervision. If you're working on engineering supervision, then you can use this table and don't worry less about all the tables in the NEC code book. You can find how much current a conductor can carry using the AmpCalc. I encourage you guys to just research and go Google it. $1,000. Ellery Beckett has one. A lot of engineering firms have it, and they use it for 24 ducts underground to carry 4,000 amp feeders, 3 or 4 of them, different locations. And how much current can a 500 kcm conductor carry under these circumstances? Well, how can they do this, DJ? Because of engineering supervision. Any question, guys? So what they do is, this is a thermodynamic equation. They take the temperature, surrounding temperature, and they find how much current the conductor can carry under these circumstances. Engineering supervision. Okay, 310.16. If you don't know 310.16, guys, too late to switch careers now. But I want to remind you for 310.16, a lot of people, guys, don't know that it goes all the way to 2,000 volts. I don't know how many of you have paid attention to this. It goes to 2,000 volts. Who cares? I had a class one time, guys. It's a steel company, and they have machines that run at 750 volt. Now, is this high voltage, low voltage? This is high voltage based on the code. This is defined as high voltage. Can I use a THH conductor? No problem. It's rated because can I use this table to find the amps? No problem. It goes all the way to 2000. Just FYI. And also this is, guys, for 3 and HOTS conductor in a raceway, in the cable, or in Mother Earth directly buried. If your situation is, does it say anything about cable tray? If you're in a cable tray, can you use this table? Does it say anything about cable tray? You can't use it if you're a cable tray. Direct cable tray or earth directly buried. Does it say what would you do in a raceway or cable or earth directly buried? This is basically what the application of this table is. Very limited. 99% of the time, guys, we are going to be in a raceway or in a cable above ground, and so it's not a big deal. Okay, how do you use this table? Quick reminder, I always use it this way, guys. Up to, I highlight, here's how, let me go over and highlight this. 60 up to this point, you're going to use 60 no matter what. If your conductors are up to number 1, do you guys remember? If your conductors are up to number 1, you're defaulted to 60. Also, if your amps are less or equal to 100 amp, you're defaulted to 60. So these are the, if you don't know anything, if you guys remember, if you don't know anything, if your conductors are number 1 or less, 60. If your amps are 100 or less, 60. When do we use then 75, Chad? You use it if your amps are more than 100 amp, okay? Number 1. And if your conductors, look at the conductors, guys. See the conductors now? These conductors go directly with these and down. Or if your conductors, as you can see, if your conductors are number 1 or larger, or the amps are more than 100, you go 75. Otherwise, you go to 60. Another thing, guys, you have to pay attention is also insulation. Insulation have to be rated for 75. Any question, guys, how to use 60 versus 75? As a default, your default is always what you're looking at. Less than 100, up to number 1, 60. More than 100, more than number 1, which is 1 aught, is 75. That's your default. Motors are exception. Please add this one, motors. Motors. If you have a motor, they default you to 75. If you have a motor, they default you to 75. So Brad, my friend, if you have a piece of machine and the machine is 60 amps and all the lugs are rated, the machines is 60 amps and all the lugs are rated for 75. You know, you bought it. The lugs are rated 75, 75. The cables are rated for 75. If you know that, then yes, the machine is less than 60, guys, less than 100, but you can use 75. Unless you know that the lugs and the conductors and the machine they're going to feed are rated for 75, that's what your default is. And but honestly, most of the engineers, guys, you default to this one because when you design, you have no idea. Okay, so the last one I want to see, then DJ, when the heck do we use the 90 degree? Only for derating. Derating. Meaning, here's an example. Can number 1 aught, guys, carry 170 amps, normal condition? No. Can number 1 aught carry 170 amp, 1 aught THHN conductor? Can a number 1 aught THHN conductor can carry 170 amps like it says here under the 90 degree? No. Why no? Under normal condition, because the 170 is there only for derating. Under normal condition, if there is no derating, no temperature derating, nothing, number 1 aught shall carry no more than 150. Am I clear about how to use this table, guys? This is the single most important thing about this table. Here's an example, DJ. You're going to go sit for your master electrician license, right? They are very keen on that one. Say you have derating and you took 175 amp and you start derate. Okay, 165, 160, 158. After you derate it, cut it, because of temperature, you end up with 158. Can a 1 aught carry 158 under normal condition? No. So regardless, when you guys derate, regardless of what you come up with, number 1 aught shall carry no more than 150 regardless. Very clear. More than 150. Let's take number 4. Here's number 4, guys. Number 4 can carry 70 amps under normal condition. Okay, can I make number 4 carry 85 amps? No, because number 4 shall not carry more than 70 amps. There's one exception, please, motors, or exceptions motors. Motors are, that's why a lot of machines that has motors, guys, they use the exception. And if you are anti-Ch and you're going to use aluminum, the same rules apply for the aluminum. I just showed the cover here. The same rules apply for the aluminum. Any question, guys, how to use this table? This is the single most important table, guys. The single most important table in any sequence book. Any question about that, guys? Here's an example. If I have a TW conductor and my TW conductor is 4 aught or 2 aught, can a TW conductor, how much current a TW conductor can carry if it's a 2 aught? 145. Why can't I go, Chad, why can't I go all the way to 175? Because I chose a stupid insulation. That's TW. Can you guys see that? So the insulation have to be rated for 75 to use the 75. Otherwise, you can't use 75. 500 kcm, Spencer. I have 500 kcm, and I decided to use a TW insulation in it. You're right under the 60-degree column, regardless. That's why, guys, most of the time we use THHN/THW. That will put us right into the 75-degree column for everything that we do. 75-degree column for everything that we do. Then all what we have to worry about now is the derating based on temperature and so forth. Any question, my friends? Any question about this? And you're not going to hear me talking about these again. I'm gonna give you guys a break in a second. Let me just go at the bottom of the table, make sure that everybody knows how to use these, and I'm gonna Mr. Bab, here's a bottom of this table, guys, are really cool. The derating temperature. For example, if the ambient temperature, suppose the ambient temperature are 230 degree Fahrenheit. I have an ambient, everybody knows what an ambient temperature is? The surrounding temperature, the normal surrounding temperature, or the adjusted because of the height of the on the roof. 230, and I, Chad Curdy, decided to use THHN, and I decided to use CU because I love copper and I can't live without it. Okay, so let's go find the derating factor based on these. I don't care about the size. The derating factor based on this. If you guys look at THHN is right here. It's rated for 90 degree. Am I derating? Yep. So I can go to the 90 directly. Why did I go to this 90, not to this 90? Because this is where the cover is, right? Here's my cover. Here's my insulation. Here's my 90. Everybody can see what? Then let's go to the temperature. This is Celsius. God forbid using Celsius. Let's go use Fahrenheit. We have 230, 230. Here's the 230. Mr. Webb, can you see that the 230 is between 132 and 140? No. Am I running out of where is the 230? We don't have 230, do we? 230 Fahrenheit. As high, you can go as high as 159. What happened after that? As high as you can go. So what's your insulation? Or derating factor? They don't want you to cut. They don't want you to cut lower than 0.41. 0.41. Who cares? Now suppose the amps for this conductor was 100 amp. Then you can only take 41 amps out of it under these circumstances. Chanel, my friend, everybody knows how to use this table for derating. Let me give you a secret. Secret, guys, now moving on. If you're using feeders, don't you ever group feeders. Don't group feeders. If you use feeders, guys, send a circuit directly. When I say feeders, 100 amp feeder, 125 amp feeder, send a circuit, a conduit per circuit, so you don't have to worry about this mess. Number one. Number two, if you're doing branch circuits, If you're doing branch circuits, guys, we use THHN. THHN, if you derate based on the THHN, if you put up to 16 hots in a THHN and you cut it by half, a number 12 conductor, THHN, still carry 15 amps. That's all what you need. So, long story short, guys, if you follow, don't group feeders, don't group the feeders, 100 amp or more, that's in my definition, commercial feeders, don't group them, because that's you screw you up. And branch circuits THHN, don't put more than 16 hots, plus the neutral included as a hot here, in a 3/4 of an inch. Don't put, which is a lot, plenty. If you stay within this parameter, 16 conductors, number 12 THHN in a 3/4 of an inch, and the feeder is dedicated, then you don't have to worry about this mess at all. Any question, my friends? Any question? Okay, I'm going to give you guys 5 minutes. I'm going to show you 2 other tables that you're going to use only 10% of the time. So if you sleep through it, it doesn't bother me, but I have to mention it because we're doing industrial. In a 3/4 of an inch. So let's look at this table, guys. This is table 310.17. We've never used 310. Anybody have used it, guys? I don't think you've used it with me, at least. 310.17. Table 310.17, guys, I want to bring to your attention. It says ampacity of insulated conductors rated for 200. Everything insulated in ambient air temperature 30 in free air. So the question would be, Brad, then where would I use this, Chad? Free air. That's if you put them in insulators, guys, on poles. Who cares? How often do we do this? Very slim. But here's where this table is very powerful. This table is very powerful. Cable trays. Remember, guys, the cable trays? So if you are to use cable trays, Article 392, I'm going to remind you guys, cable trays. Cable trays are Article 392. I'm not going to review cable trays with you, but I'm going to remind you, if you have a cable tray that looks like this is my cable tray. My cable trays looks like this. And if you guys put conductors, here's conductor 1, here's conductor 2, here's conductor 3, conductor 4, and 5 right into this cable tray and tie them together. All right? Here's a cable tray carrying multiple conductors. Could it happen? All the time in an industrial, guys. And the condition to use this table, there's a few conditions. One, I want to mention it to you. If you leave a space of 1 conductor between the conductors, so it's a cable tray, you guys know it's a tray full of cables, but don't pile the conductors on the top of each other, Jim. Leave a space of 1 conductor between them. That's going to happen, right? And in cable trays, guys, we don't use less than 1 aught. We can't put anything less than 1 aught in cable trays anyway. We're talking about big conductors. Where would you use a cable tray? If you decided to use 2000 kcm conductor and you don't want to pull that baby in an EMT conduit, a cable tray would be perfect for this type of conductor. A 2000, a 1000, a 900, a 700 kcm, but in a cable tray, perfect. Because why? Cable tray, guys, are open. So you just lay them and tie them and off you go. Okay, so if you were to use a cable tray, guys, in this application, if you don't believe me, go to Article 392. It will tell you that you use this table to find it. So suppose that these conductors, guys, suppose each one of these conductors was, just for the sake of argument, is 4 aught. how much current these conductors can carry under these circumstances if I put them in a cable tray and they're 4-aught. Now remember, Brad, we said 4-aught. Anything higher than 1-aught, we default to where? 75. So I'm going to default to the 75. And the insulation, oh, by the way, it's a THHN. And I'm not derating, no derating. So I put this in a cable tray. You don't derate if you do them this way. So I'm going to go and find 360. Spencer, do you have your code open? Can you find how much current a 4-aught can carry from table 310 to 16? From 310 to 16? 230. Do you see something different here? 360. Is there a huge amount of current? More? Can you guys see the difference? From 230, thank you, Spencer, from 4-aught, if you go to table 310 to 16, it will carry 230, right? 230. If I'm to use this table based on a cable tray, how much current can I carry from this baby? 360. What's the difference? 230, 360, 130 amps extra. Is that cool or what? 130 amps from the same conductor, the same insulation, the same conductor, the same insulation, the same ambient temperature. Can you guys see that? See where the cable tray becomes big deal? What's the disadvantage of cable tray? Expensive. Can you guys see where this table becomes a big deal? Everybody see that? Where do we use this table? Or if it's a cable tray, or if you put also power lines, like you put power poles and you carry conductors on power poles. And I think you understand why, guys, they allow it to do. Everybody knows why? Because if it's a cable tray open like this, is there any entrapment, or is the heat, will the heat be trapped in a cable tray when it's open? No. Oh, by the way, if you cover the cable tray, Spencer, and you go to the article, they tell you have to do it, I can't remember, by 70% if you cover it. But this is just open cable tray and one conductor, and you leave a space of another conductors between them. You don't put them even side by side. If you put them side by side, you use the table, I can't remember, it's 0.8, you have to do it again. Can you guys see how powerful this table is? Now, what's the rule of using it? The same rule, guys. The same rule, 60, 75. You don't use in cable tray smaller than 1-aught anyway. So this is not a cable tray. When it comes, these sizes are meaningless when it comes to cable tray. You don't use them with cable tray. Any question, guys, about this table? Very powerful table to use. The first thing comes to my mind is cable tray, Mr. Bell. In an industrial application, perfect. So bring this to your attention. So that's what I wanted to bring, this table, just because we have never done that. Using is really easy, like the other tables. And I also want to bring to your attention, guys, underneath this table, there's also a temperature derating. The same temperature derating, we derate from this table the same way. So suppose that, Brad, the cable tray was in an ambient temperature of 150 Fahrenheit. Then you're going to go size a conductor under 90-degree column, derate it based on 90-degree column, and cut it based on whatever application. Suppose we have, what do you say, 150? 150 will put me right in here. Suppose, where did it go? Did it go down? Okay, let me see here all the way. This is cable tray. Suppose that my cable tray was, what did you say, 150 here, and my derating factor is 0.58 because in the cable tray that you guys have seen, I use a THHN, which is 90-degree THHN, so my derating is 0.58. Still the same derating. Cable tray, temperature, same derating. Bundling is different. Temperature, same derating. So really the same derating in terms of temperature, Mr. Bell. Okay? All right, I'm going to take you to another table that you would use, not as much. This one, if you're lucky enough to work in a steel melting, as I said, North Star Steel, guys, I do a presentation there, and all the cables that they use is this Z cables and type. What do they do? What's their business? Camille, my friend, they take your car and my car, pancake it when it's gone, chop it into pieces, melt it, and make rebars to build bridges and buildings. That's what the business that they are in. So if you are in a business like this, hot, dirty environment, very hot, and you need to use a wiring system, this table becomes very handy for you. I want to bring to your attention, guys, a few things. This table, again, insulated conductors. up to 2000, no problem. And look at the insulation though, 250 all the way up to 250 kcm, 3 current conductors in a raceway or a cable based on ambient temperature of 40. Every ambient temperature that you have, guys, every ambient temperature that we have is based on 30, except one or two cables based on 40. Very hot. Everybody knows what a 40 Celsius is? That's hot. Okay, so let's see how it works this. Look, Spencer, I want Spencer to do me one more favor. Here's the 4-aught, the same thing that we talked about. Insulation Z, and insulation Z, believe it or not, it's rated for 150 degree. 150 degree, guys, Celsius. AKA 302 Fahrenheit. 302 Fahrenheit. That's hot. So suppose I use this Z insulation. Spencer, can you tell me how much current if I use this one, that conductor can carry? No, not Z. Based on, we just picked it up, guys. If you take 4-aught THHN, it will carry 230. Look at this. Look at this. 230. Look at this. 332. Do you see the difference? 332. Why? Because they use a special type of insulation that you can heat these conductors so much and it wouldn't deteriorate. And oh yeah, if that's not enough for you and it's too hot, I will use an insulation of rated. I can go all the way up to this 250 insulation, 250 insulation and nickel. They use now nickel instead of copper, nickel, and they use nickel coated cover. And I will use a TFE insulation, and the same conductor can carry 361 amps. By the way, 361 amps, guys, only for derating. Only for derating. Only for derating. So when you start derating, you start by 361 amps, cut. And Spencer, the 4-aught under 75 degree column gave us how much again? Based on 310 to 16, 230. So no matter what you come up with, guys, you still can't go more than 230. And here's, let me show you a very interesting situation. Here's a log here, and here's a log here. This log is rated for 75 degrees Celsius. This log is rated for 75 degrees Celsius. In between them is a big fat cable. This is a big fat cable that I decided it's going to be TFE cable. And this guy was a 4-aught. So how much current this guy can carry based on this situation? 361. 361. So 361, guys, but because the ambient temperature was so high, I started derating. So when you start derate, you start with this amp, multiply it by, let's multiply it by, suppose down from the bottom here, based on the temperature. Suppose, guys, I came up with 0.7. Anybody can do that? 0.7 times this. Have a calculator. So if you guys have a 361 times 0.7 equal 252. So this will give me 253 amps. Spencer, do you remember that number? 4-aught can only from 310.16 can only carry 230 under which column though? 75. Yeah, 230 amp. Now look at this. So I can, based on the rating, 253 amps this can carry, but the lugs, guys, are only rated for 75. So if I'm allowing this one to carry 253, no problem for the insulation, but guess what? The lugs are going to get loose, get hot. Long story short, you still have to, you're governed by the 230 because of the lugs. Can you guys see that? So the question would be, Camille, then who cares about all this calculation? Well, why should I use it? If I'm already governed by this, it allows you guys to put conductors in a very hot environment, derate them, and you still come up with really good amp conductor. You know what I mean? It allows you to first put insulation in very hot environment and don't have to oversize them hugely because of the insulation. If you do the same calculation based on THHN, you're going to find that it's going to be a very small amount of current that carried from the THHN. Any question, guys, about how to use this table? Where would you use it? In very hot environment. What's the ambient temperature? 104. Only if 104, you encountered 104 all the time, guys. Temperature, that's a good application for it. Steel melting plants is a good application for it. Boiler rooms is a good application for it. But you have to specify the TFE insulation or the Z insulation if you're using copper, or SA insulation and so forth. And if you want to know what Z insulation, you guys remember the 310.13a table? That will explain to you what the Z insulation is. All what we care about, it's rated for 150 Celsius. Any question, Mr. Webb? So this is a high, they call them high temperature cables. High temperature cable. You can Google them, high temperature cables. So that's a table that you will encounter, and the reason why I bring this one really just because here's the derating factor under this table. The same application for derating factor, guys. Same application. How to derate based on Fahrenheit and Celsius, same application. Suppose I'm using TFE, and suppose my conductor I'm using a TFE insulation, and suppose the ambient temperature was in Fahrenheit was 350 Fahrenheit, degree Fahrenheit. Here's my 350 right here, Mr. Bab, and that will take me all the way to right here. So my derating factor is 0.58, right? Did I do it right? 350 up, 350, they'll get your derating factor 0.58. Same way. So that's this table I want to bring to your attention, my friends. This is another table, since we're in the industrial, another table that's the same thing, guys. High temperature table, Z insulation, based on in free air this time. This is in free air. The only difference between this table, guys, if you look here, this is for in free air. If you don't put it in a conduit, just put them in a free air. And also cable trays will take this one. Same application. So moving on to okay, this is a bit of these. Okay, supported by messenger. There's a few applications here, guys. I'm not going to go over them. Messengers and total, these are but the most important things. Let me go to the second one I'm going to highlight, guys, as high voltage. High voltage, 13,800 volt. So these are rated for 50 kV and 5 kV. When you have cables high voltage, guys, here's the table that you use. And I know we use a few of them here. Let's go straight into a bunch of tables. A couple of things, guys, that you use: electrical ducts. They give you a combination for electrical ducts with high voltage. The same thing for low voltage. If you guys look at detail number one, this here could be a duct, concrete encased duct. Why do you think you encase a duct in a concrete if you are high voltage? Are you kidding me? Do you want somebody to cut through that duct? And the duct could be a PVC. This is single conductor or multi-conductor cable. It could be one conductor cable or multi-conductor cable. The same thing, guys, here. It could be single conductor or multi-conductor cable. This one is the single most important one, guys. In this case, I can have a multi-conductor cable, 2 circuits, circuit 1, circuit 2, or as a matter of fact, I can have 6 circuits, 3 multi-conductor cable here, 3-phase cable, 6 conductors, 3-phase each in one combination. All of them are ducts. Spencer, look how far they move them away from each other, 7.5, 7.5, and in between them, this stuff, what do you guys think? This is concrete encased. Concrete encased. That's most of the time when they go underground, how they do it. You put them PVC conduit, they put them in a spacer, they have a spacer for them, and they put concrete in between them. They space them and they pour the concrete right in between them. And it becomes concrete encased ducts. And they pull the conductors through them. Put them underground, Different application, look at this, you can put them in any application, as you guys can see. Now, who cares? I want you guys to look at the detail. Here's detail 1, detail 2, detail 3, up and down. These are details. The tables care a lot about the details as you go through to the tables. And again, very few guys with you will be able to. Here's if you direct bury them in earth. So you put two circuits. This one is multi-conductor cable direct buried. These are multi-conductor cable direct buried. Look at this, the same thing, glue them together. Different configuration. Parallel circuit. Look at this, the word cable or cables. Can you guys see the word cable or cables here? So it could be one cable or multi-conductor cables or cables. So all these, I'm going to bring to attention all the way to detail number 7, and I'm not going to go over this one. Very few of you guys will be using, but I'm going to show you, Mr. Urbab. These are very important for industrial, and other than industrial, probably I wouldn't mention them if it wasn't industrial. The same thing, oh yeah, by the way, can engineers do a different calculation for medium voltage? Yes, engineering supervision, you can use this table to come up with different application. All right, here's the first 10. I'm going to go all the way to, there's a few of them, guys. I'm going to go to my favorite, which is this one. If you have insulated single conductors in air, let's look at this one. This is insulated conductors in air based on conductor temperature of this and ambient temperature of this. This is up in the air on the poles, up in the air on the poles. So suppose I have, guys, a 13.8 conductors, and I put them on the pole. Right, here's my conductors. They're sitting 1, 2, 3 conductors, and this is my pole sitting here. And my conductors were 4-aught. If I pull them and the insulation is medium voltage, insulated for his medium voltage, this is common, medium voltage 105. Look how much current they can carry if I use this insulation, 445. Do you remember, Spencer, do you remember how much 4-aught can carry? 230. Look how much this can carry, 445. Are you kidding me? Anything less than number 8, don't you even think about it. They don't use in medium voltage. Any question, guys, how to use this one? If you used a cheaper installation, which is 90-degree rated, you still can get 400 amps out of 4-aught. Remember, guys, 4-aught can give you 230 THHN. 400 amp if it's a medium voltage cable. The installation will be medium voltage installation. And I'm going to bring to your attention, guys, this is 15K, this is up to 5K, and if you are one of the lucky ones who are going to go all the way up to 35K, look how much you can carry. Same amount, 445 amp. Say, suppose I'm going to be using, 34.5 kV system. That's another system that they use, 34.5. It will sit you right in here. Suppose I decided, because I don't care about money, I will use this insulation. You can use either. By the way, 105, the only difference is more money on 105. You can get 445 amps from a 4-aught cable. Any question, guys, about this? Again, the reason why I mentioned this one, because it's an industrial application. You guys we're doing industrial. Close this one, go to here, and I'm taking pictures of all these, Mr. Beb, put them in the network. Okay, now we're going to go put them in underground ducts. Let's go all the way to the underground ducts, guys, all the way. And there is a few application. I'm just picking 70. I'm going to go to 77, my favorite. 77. There you go, 77. Okay, do you guys remember 77? Look what 77 says. Let me just see all the way up. There you go. It says the ampacity of 3 single insulated cover conductors in underground electrical ducts, 3 conductors, pure electrical duct, 3, based on the ambient temperature of earth, 20, electrical duct arrangement based on the arrangement that you can see, 100% load factor, thermal resistivity of 90, and conductor temperature of 90 or 105. It might grieve to some of you guys, but let me tell you. If you put one circuit, can you guys see one circuit here? Suppose based on detail number 1, you guys remember how detail number 1 was 1 duct and 3 cables in it, just 1 duct, 3 cables. Look what you can get. If I have 1 duct, 3 cables, if I have 4-aught, and I decided, Chad Carey, to use this insulation, that will give me 310. Spencer, 4-aught can get you what? 220. 310 if you put it in underground duct. It used to be 400 a minute ago. Now it went all the way to 310 if you put it underground encased in concrete. If you're in a higher voltage, like this one, guys, all the way up to this, the higher voltage, remember, you can go all the way 350, you get a few amps, 5 amps. Any question, guys, about this? So that's one. That's the most common one, and you guys use this one for me. And I want to go all the way to the detail, my favorite detail that we use all the time, detail number 6. Look at this, guys. I'm going to go all the way to detail number 6. This is very common. You guys remember the detail number 6 used to sit like this, here, here, and here? That's a detail number 6. And there's a circuit inside each one of them and concrete around it. Okay, here's the detail number 6. I have 6 circuits, 6 parallel circuits. It doesn't have to be parallel. 6 circuits, medium voltage. And I, Chad Carey, decided, since I'm not paying for it, the system here is 13.8 kV. So that will put me under this situation. Can you guys see that? And because I'm not paying for the installation, we'll use the most expensive one, medium voltage 105, rated for 105 Celsius. And I decided I'm going to pull a 1000. Well, let's continue with the 4-aught, because the 4-aught, Spencer have been generous enough to tell us the 4-aught how much it's going to give us. 4-aught, Spencer, look at the 4-aught here. 205. How much 4-aught gave us normally? 220 or 230? If I put 4-aught, 3 conductors in each one of them, guys. Remember, the 3 conductors in each one of these. 3 conductors. In this arrangement, look how the amps went down. Anybody knows why the amps went down? Because the heat interaction. There will be a heat interaction between all of them. The entrapment of heat. You trap the heat in this block of concrete. Any question, guys, about this? Can you see how the 4-aught now went from 400 amps up in the air into half of it if you put them underground? Now you understand, Jim, why the electrical utilities would rather put their cables overhead. They get more amps out of them because of natural cooling of the conductors. You trap them in Mother Earth. What happened? Heat. You trap the heat with them. What happened to the insulation? Insulation deteriorate. And of course, it's twice as expensive, guys, to put a medium voltage cable underground than put it overhead. That's why the utilities, the cheapest, bring to your house and mine and all the stuff, they put it overhead. Twice as expensive to put the same feeder underground versus overhead. And why? Because look at the amps. We went from 400 for the same conductor, 4-aught, guys, 400 amps, down to what? To 205 amps. Any question, my friends? Any question about these? If your system was 4160 volt, this is another common system, 4160 volt, then I'm right in here, right? My installation, say I will use medium voltage 90, and I can only get 195 amps out of if my system was for 4160 volt. Everybody can see how based on the system you go up. There are 2 systems here, up to 5K, anything up to 5K, and higher than 5K to 35K. Can you guys see that? These cables, guys, they come with 5K on them or 5.5K. It says 5.5K installation. I have one of these cables in my office if anybody will look at them. Any question about these medium voltage cables, guys? And again, I wouldn't usually show this unless it's commercial. This industry, you're going to be in a situation where they need a medium voltage feeder. The first thing comes to your mind as if you need 6 circuits, here's what you do it. If they only want one circuit underground, guys, if they only one circuit underground, concrete encased, you're right in here. If it's only one feeder underground, one circuit, detail 1, and this is the best. Here's 4-aught. Here's how much current it can carry. Done. If the voltage is within this voltage limit. If it's within this voltage limit, then 350, which is not a whole lot of difference. Any question, guys? So these are very, very interesting ones. The last thing I want to show you guys, and then I'm done, in the ampacity for good. If anybody wants to discuss anything else, I encourage you to do so. I want you guys to go. I want to go all the way to Annex B and show you the same details. Annex B, page 701. If I can get myself to go there, Annex B, all the way to Annex B, Annex B, and I need what's this? Annex B, electrical ducts, examples. Okay, formulas. Okay, here's my Annex B. Okay, let's go. If you guys go to Annex B, Annex B, I'm almost done here. Put you in a. If you guys, I want to go for, in particular for Annex B, guys, a table that says very few people have done that. Say B310.7. If you guys go to B310.3, B310.5, B310.6, B310.7. There you go. I want you guys to look at this table. Now, this is where you technically have to use this table. Very few people go there. Let me just, this is for 3 single insulated conductors up to 2,000, right? Underground ducts. 3 conductors per duct, current based on ambient temperature of 20. Electrical duct arrangement is right here, and the conductor temperature is 75. This is for low voltage. Now let's say, let me go to detail number 6, which is detail number 4. Detail number 4, 9 of them. So as far as you can get, detail number 4. Detail number 4, 4, 4, 4, 4. Where's my detail number 3? Detail number 2. Detail number 3. Okay, let's just look at detail number 3 because it's there. I want you guys to look at detail number 3. Detail number 3 is actually 6 parallel sets. Detail number 3, it's 6 parallel sets low voltage. Suppose I'm paralleling again 4-aught, Spencer, back to the 4-aught, and I'm cover because Chad loves cover. And the arrangement detail number 3, guys, looks like this: 1, 2, 3, 4, 5, 6. Here's detail number 3. And how many conductors? 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Here's detail number 3. I decided to put 6 circuits encased in concrete. And all of them are low voltage circuits, 600 volt or less. And each one of them is carrying 4-aught. Let me just, so if you guys go to 4-aught, look at this. There's a load factor and thermal resistivity. I always default under detail number 3. The thermal resistivity of the earth is 90 and load factor of 100%. 100% load factor means, guys, they all will be hot at the same time. All of them will be hot at the same time. Brad, where would you use a 50? If you have guys in 4,000 amps, they have tie. If they have 2 tie, 4,000 amp here, 4,000 amp here, so you either energize from this or energize from this, but both cables are right next to each other. Then each one of them you put it at 50, because based on the design, because it's a tie, 4,000 amp tie, it would never, the tie and the main would never be energized at the same time. So that's where the 50 is. So in our project, for example, guys, we're actually at load factor of 100%. So all the way, Spencer, my friend, I'm picking on you here. Look how much current we can carry under these circumstances. 175. Spencer, can you remind us how much we can carry under normal condition? 230. 230. So from 230 amp to 175. To 175. If you put your conductors in an underground ducts and encase them in concrete. A lot of people, guys, use 310/16. When you guys size the 4,000 amp switch gear for me, use 310/16. we shouldn't use, technically, we should be using this table. Any question, guys? Any question? So that's basically it. If you put them under 6 ducts, which is detail 3, 3 electrical ducts or 1 duct, these are encased concrete ducts. Why would you encase them in concrete? Protection. Protect them from somebody cutting right through them. And Spencer, do you think you can put these 6 ducts at the top of each other without concrete, and you just bury them with earth, and you think they're going to stay there? If you guys don't put concrete, what happened 2 or 3 years? It's going to settle down. Somebody's going to drive over this one. They're going to bust them. The reason why we put them in concrete, because these could be under a road or something. If you don't put them in concrete, somebody drives over them over time. They're going to settle down. And you're going to bust them if you don't encase them in concrete. It's another reason why we encase them in concrete for that size of a feeder. Okay, does that make sense, guys? I'm just trying to bring to your attention, when you start dealing with 4,000 amp, be aware how you're going to lay out your conduits. How are you going to lay out the 4,000 that we have, guys? We have 11 runs. How are you going to do 11 runs? How you can't even, the code doesn't talk about 11 runs. Well, you can either use 11 runs, will give you 2 of these. So I would use, here's one set and here's another set, right? Here's 11 runs. 1, 2, 3, 4, 5, 6, right? So basically, I'm using 2 of these side by side. That's how you're going to carry the 4,000 amp switchgear for Chad, the 4,000 amp switchgear based on 11 runs with 2 sets of 16. And how are you going to size it? We're going to size it based on what conductor should be sized based on this, which you end up with a bigger conductor. What we did, guys, at Elevator Bucket, when we size them, we always size them based on an amp calc, a software that we had, Spencer, it's called amp calc, and it comes with the same calculation, by the way. But you can build these are 12 ducts encasing concrete, one system, 12 ducts. The code doesn't talk about this. There's nothing in the code talk about 12 ducts. If you look at all this, no 12 ducts encasing concrete at the same time, nothing. So what do? We build them in a software that's called amp calc. But if you don't have the amp calc, what would you do? You either sit and cry, go to the bar and drink, unless you're Alcoholics Anonymous, or you can use these 2 sets. I usually use the 2 sets, and use your application best. Assume they're going to be the same 2 sets, and basically apply that rule here. Okay, so the last thing I want to show you, and I promise I'm going to shut up here. Let's go to the 400 amp, Spencer. The 400 kcm. Here's my 500 kcm. It's a copper, and I'm going to use detail 3, 6 ducts, detail 3, and I'm using, of course, the EWI-Ch. It's underground. Are you kidding me? And I'm going to tell you guys, and I'm going to use copper EWI-Ch under these circumstances. How much can carry? Look at this. 273 amps. Anybody can tell me, guys, how much number 500 kcm carry under normal condition? Normal condition is 380 amps. Now, Spencer, if you put 500 kcm THHW in this arrangement, which is this 1, 2, 3, 4, 5, 6, you can't use 380 amps. You're going to use 273 amps. 273 amps. Any question, guys? So that will get you bigger conductor size. You size bigger conductors when you carry the 4,000 amp. Now, if you take based on this, guys, where's my calculator? If I have a 4,000 amp, here's my 4,000 amp divided by 273 equal, I need 15 runs to size it. A lot of people have used 380, guys, as kind of a rule of thumb, but it's really not. What we did, again, at Elevator Bucket, we use a software called AmpCal. We build the system. We have 12 duct system. I want to carry them with 500 amp. 12 duct system will ever run it, and we see how much conductor, what's the size of the conductor, and how much current the conductor can carry under these circumstances. Any question, guys? These are just start to think about. Not, it's not enough to. This is table 310.16. Does not apply all the time. It doesn't apply for this application. If you have a 6 ducts like this is how much current you can carry out of these conductors, 273. Let me get you a little secret how people can hide and justify it. Just a little secret how people can hide and justify it. Can you guys see this value here? Anybody saw this value here? 412, 318, 412, 275. Now what the heck is 412? 412 is a load factor. If your load factor is 50%, meaning if the conductor is going to be only 50% loaded, you can load it up to 416 amps. Or if this conductor is going to be loaded and the one next to it's not loaded, you can carry it 416. So a lot of people guys say, okay, I have all these 6 ducts. What's the likelihood that they're going to be carrying really 4,000 amp in real life? Most of it is just addition and pumping them up because of safety and all this stuff. In reality, when everything is up and running, you're lucky if the 4,000 amp cables, guys, are carrying. You're lucky if they're carrying 60% of their load. You're really lucky if they're carrying 60% of your load in real life when you energize everything. That's why a lot of engineers, between these two values, what happened? 380s between them. So you can kind of let go with the 380, knowing that really it's not going to be carrying, they're not going to be loaded after I energize the system. Any question, guys? Any question? So, Spencer, my friend, if you use 380, just know that, by the way, that if anybody justify, if you want to write it down, just say, well, this after we energize the system, it's highly unlikely that the system is going to be really fully loaded. All the conductors are carrying a 4,000 amp, highly unlikely. Why? Because the diversity of the load, guys, unreal. We designed a 4,000 amp switchgear, DJ, my friend, and when you energize, you go measure the amps on them, and you're finding 1,600 amps on it, or 2,000 amps, or 2,500 amps on it. And it's designed for 4,000 amps. It is what it is. When systems are energized, there's certain things with the air handling unit, you have 5 of them, they don't kick at the same time. You might not, very small amount of time, guys, that you're going to pull closer to 4,000 amp. Very, very small amount of time. Because of safety that we bought and all this good stuff. Anyway, that's my justification for when we have to use 380. Any question, my friends? A lot of people don't know that these exist, these tables, guys, in the end. Holly, have you guys used them ever? No.
You've been showing them whatever.
Yeah. Okay. That's all I have, guys, about the ampacity. Basically, there's a bunch of them in the back. They're all the same concept based on underground ducts. Any question, my friends? Any questions? Okay, this is the first and last time we're going to hear Chad talk about ampacities for conductors. Hopefully it sinks in. Well, in terms of that detail, talk about tables. Thank you. Go eat.